For people that are around tonight, if you're looking for something to do, I think some of us are going. There's a 7 p.m. volleyball game with the university. So if you're interested, I guess talk to me over coffee break, and we'll keep you in the loop. All right. So our next speaker will be Guy Blelloch, who's speaking about parlay hash.
Yeah, contrary to the schedule, which says I'm talking about high bandwidth memory, which I believe was actually Kunal's talk, right? Yeah, so this is work I actually did at Google with my collaborators. Siddhartha used to be at Google, and Kuba's at Google, on concurrent hashing. So our goal was to come up with, it turns out at Google they don't have a common concurrent hash table. Instead, they've got 8 or 9 different hash tables implemented by 8 or 9 different groups over time, each with different advantages. Some are good at reads, some are good at writes, some are not good at all. And so, our goal was to come up with a general purpose concurrent hash table that could, serve as a library. This hasn't happened yet, but we're still working, trying to get this to happen. But what do I mean? So by general purpose, it has to be, the standard concurrent model, fully asynchronous, so it's deletes, probably a few more operations like iteration, et cetera. It has to be growable, so it can't be a static size. And importantly, it has to have arbitrary types. So unfortunately, most academic papers and concurrent hash tables only support integer types or something of that flavor. In fact, I've looked at all the code and I haven't found an exception to that yet. And then, of course, they have to be efficient, but they don't have to be just efficient in one situation. They have to be ideally efficient in most situations, okay, or as efficient as they can be, So they have to be efficient both in terms of latency. So often people in Google especially, they care about the latency because they're often replying to requests that's coming online. They have to work on both low and high thread counts. They have to be, work under high contention, even if a lot of, accesses to the same location. They have to work with high and low update rates, small and large sizes, and in particular, you have to work under oversubscription. So a lot of jobs at Google get served out to servers, and often there's more threads that get scheduled on those servers than there are, software threads than there are hardware threads. And so you have to worry about things getting swapped out, which then makes lock-based solutions particularly problematic because you get the standard problems with locks and someone hogging a lock when they're swapped out. There's of course been a ton of prior work. Erez says I had to put some prior work on hash tables, growable hash tables. So at the top here is a bunch of papers that appear in conferences from people that we know, these are all growable tables, and there's various different methods, and they have various guarantees. Some are lock-free, some are wait-free, some are lock-free when they're not growing, but maybe take some locks when they're growing. There are various different features to them. The issue with all these, like I said, they only work with integer types. I dug up the code for all these, and I didn't find an exception to that, or some trivial types. Some of them, the performance okay. Some of them are more interested in the theoretical guarantees, and they're not practically that efficient. There's also a whole bunch of libraries. So Meta has their Folly library. I don't know if any of you've used it. It's a public, domain library that has all sorts of different tools in it. And one of them is a concurrent hash table. So they've, optimized that over the years. Threading building blocks is Intel's concurrent hash table. Boost is a C++ library. It has a concurrent hash table. There's libcuckoo, Java concurrent. So there are a bunch of concurrent hash tables out there. Some of them are very recent, just from the last year or so, and a lot of them are, a lot of people spend a lot of time optimizing.
Can you briefly comment on why general types are much harder?
It's not necessarily. In fact, I don't know. In some of these here, general types would be much harder, and some of them it's just the way they coded it up. which means it's hard for us to then run a set of benchmarks on them because that's the way. So I haven't teased out which ones suffer from those. But some of them do, like atomic swaps on the key value pair, and then that key value pair better fit in, in fact, I think a lot of them do. So that's one particular problem. Okay. Then we have this 90-10 rule, which is always true for any concurrent algorithm, or in fact, even probably any algorithm, is 90% of the design effort, if you're trying to get high efficiency, is going to be on 10% of the instructions, the memory instructions, right? So that's, of course, what this workshop is about. And indeed, we spent all of our time, and the particular, what I'm going to be talking about today, which is one particular part of the hash table we designed, is exactly to address these issues. And of course, these are all topics which have been covered in this workshop. Cache locality, I'm not sure there's been a lot of discussion about cache coherence, but that has to be dealt with. There's contention. I'm not sure how much was discussed about that, but when a bunch of threads access the same location, it's highly contended. They each get slow. There's the TLB. There was some discussion about the TLB. Safe memory reclamation. There was discussion about that. Then there's the OS that gets in the way, and you need this for allocating new chunks of memory. Basically, that's the only way you can get memory on a machine. And then, of course, there's all sorts of fancier machines we could consider. We're just considering here a standard multi-core, but we still have all these other issues. So if we look particularly at a concurrent hash table, what are the issues that come up? Okay. Well, the first one is, we're not going to find what we want in our first try, right? We all know that. Might have to go down a linked list or linear probing or something. Ideally, we'd like to still only have one cache miss. So if we're going to try a couple things, we'd like to look at them and find them at, one or maybe two cache misses, right? So most of them should be, on the same cache line, and I'll talk more about this. We want to avoid indirection. Okay, a lot of these theoretical ones, in fact, the reason they're not that practical is they all have these great theoretical bounds, but they all rely on levels of indirection. Okay, which, getting to your point about types, is if you put a pointer, then it's easy to deal with a level. If you have a level of indirection, it's easier to deal with general types than if you don't. In fact, that's a lot of the topic today. We want to avoid fences, so safe memory reclamation requires a fence. You have to announce yourself. And that can be expensive. You want to be careful with, especially careful with locks when you have high contention. These locks really fail under high contention. And then you have to be very careful about when you go to the operating system. I'm going to be focusing on the first four of these, and in particular, a particular approach to deal with this getting stuff on the first cache miss while still being lock-free or weight-free and performance. So let's go and look at some how modern sequential hash tables work. Okay, the fastest hash table out there right now is Abseil Sequential, which is Google's one. There's also Follies has, in addition to the concurrent one I mentioned, they have a sequential one, which is almost as fast. In fact, it's more memory efficient. So the Follies more memory efficient than the Google, Meta's one's more memory efficient and Google one's faster. But they both have a similar idea. They both break things into blocks. In fact, I think all the fastest sequential algorithms have this idea, is where you break them into blocks and you try to make, in the common case, you're going to find it within this block. So instead of hashing to a particular location, you hash it to this bucket which contains a whole bunch of things. Okay? And then what they, in fact, both the Meta one and the Google one, they have this second level hash, which is a 8-bit hash on the key. So they first go to the block, and then using a vector instruction, they compare it to all the entries in this block in one instruction, and they can figure out where to go. They go to that one thing, and then they're there. Okay. And so often it'll be, these blocks are, it'll be one cache miss because these entries, at least the first few, are going to be on the same, or maybe it'll be a second cache miss if it's, further on the back block. But at most, two cache misses. Okay. And if you look at, and the other nice thing, and the other reason, we also try to avoid TLB misses, right? So even if you have to access 2 or 3 along, cache lines here, you're almost guaranteed they're on the same page. So at least you only have 1 TLB miss. Okay. So then you look at the abseil, which I could say is fast, and it's a similar idea. The only difference, instead of having a separate header word, a separate word per block, they keep the headers in a separate array. Okay, but otherwise it's a very similar idea. And you say, well, the separate array, maybe that's going to cause 2 cache misses because you have to go here and here. But it turns out this separate array only has 1 byte per bucket. And typically that can fit, at least if you have up to, nowadays you've got a couple hundred megabytes of cache. So this is going to fit at least 4 tables up to, a couple hundred million size in cache, this metadata. Anyway, so that's how, so the importance here is just that they have some way of blocking it and keeping it, making sure. And then, of course, if you run out of a block, then they have some way to overflow. But that's the uncommon. The goal is to make that the uncommon case. So they're sort of optimizing for the fast path, which is when it's within a block. So if we just look at some performance, yes, these things get much better performance than for example, STD hash is the C++ hash table. They're almost 3 times faster. Foley is twice, and this is 3. And they also save a lot of space. Like I said, Foley is more space efficient, and abseil is faster. Question? Bill? No. These are all single-thread numbers. These are single-threaded, sequential hash tables. Any questions at this point? So what we'd like to do is mimic this kind of performance in a concurrent setting. Okay. There's this old idea which is called sharding. And so what you can do is if you have a sequential table, you can basically break up your space. This is you hash to some index. You break up the index space into blocks, and then you can tune how many blocks you want. And within each of the blocks, you have a sequential hash table, okay? And then all you do is, if you wanted to do a read, you would take a read lock on the block, your appropriate lock, and then you just do the sequential read. If you wanted to do an update, you'd take a write lock on the block, and you do your update, okay? So it's kind of a simple idea. It does require a level of indirection, but so that's going to add some cost. But actually, the bigger problem here is these locks. And they're actually not too bad under low contention. But under high contention, they suffer terribly. So here is, didn't I have a set of work? Oh, I should mention here that these numbers are, again, we talked about at the beginning, we wanted to work under all sorts of different scenarios. So this is under different size. This is a geometric mean, these numbers over different sizes, different update rates. Zipfian is the contention rate. It says how many queries go to the same point, and then different types. So this is the...
Considered large?
What?
Is 10 million considered large?
It probably not. I probably could have run these numbers larger, but it would have taken longer. Yeah. And 10 million on the machine I was running out was big enough not to fit in cache, so it was not cache. So you look at this, and basically it goes from something I believe it's like 20 here, or 18 or something, up to 120 on 128 threads. So it saturates very quickly. And if you look at this in more detail, this is a geometric mean here, what can happen is actually if you have very low contention and read-only, first of all, if it's read-only and low contention, you can actually get 40x speed up, okay? The problem is when you have high update rates and high contention, those locks really get you. Okay, and this isn't even with oversubscription. So oversubscription is when you have more software threads than hardware threads. This is lock-based, and so would even suffer much more if we went into the oversubscription case. So it doesn't really work. Although I should mention, this is how maybe a third of the ones at Google had been implemented.
So, so as you go from 50 to 125, you get very little
little benefit. Is that?
That's right. Yeah, you basically, what you're getting is you're getting benefit up to about 8 or 16, yeah, up to here, which is 16. And then even when you go to 32, you're decreasing 64. I should point out there's only 64 cores on here and 128 threads, so you might expect it not to get that much speed up here. But certainly you'd expect it to get up good speed up to that point, and it's not. So you're only getting about a 5.5 speed up on 64 cores.
Z equal to 0.99 is a typical value?
0.99 is what's considered the ZipVM appropriate for the English language. So that's sort of, if you model the English language and the density of words, that's the ZipVM parameter for that.
So does Google have so many updates, like 50% updates in their workloads?
It depends. So again, this is supposed to be, so some of their applications don't. Some have equal updates as loads. Like I said, this is meant to be a general purpose library. So some of the libraries out there do very well at read-only, and indeed their application is only read-only. So they're probably okay for what the application is. So let's look at another possibility to try to get the same advantage. So, if we go back to this idea here, or even the better picture is here, the problem is if you start thinking about trying to make this concurrent, you have to update a whole bunch of things at the same time, right? Because we have to, if we're going to have to update some field here, we're going to have to update some field here. It turns out there's also this overflow here, which has to do with if someone overflows a bucket, what you do. There's a whole bunch of things on here that have to be updated atomically in order to do this. And so we want to do this efficiently. Not only that, but you also have to read them atomically. Otherwise, what if you read and say, oh, look, I found a hash miss here. I go to the field here, and you think it's the right one, and it's wrong, and you could get, seriously messed up. So the observation is most of the time you're accessing just one of these blocks, and you're going to do a read or write or maybe a cas on just one of these blocks. Okay. So what if we can load and store these blocks atomically? Okay. And that's really what I'm going to spend most of the time today on. So the idea here is, what if we can take this block and we can sort of load it out atomically, do our computation, and then change it and swap it in atomically. Okay. Now it should be obvious we can do this with a level of indirection, right? That's the oldest trick in concurrent algorithms, right? We have a pointer to this, we point to this thing, we update it, and we then cas in a new pointer. Okay. But that's exactly what we're trying to avoid, right? So then why would we even do this trick at all? We wouldn't, right? We'd do something else. So we want to make sure that we can do this while the reads still just read directly on this value. Okay. So what this is what we call a big atomic. It turns out that C++ actually supports this, at least for trivial types, trivially copyable types. In C++, you can put a multi-word trivially copyable type. So this could be a structure with 10 integers in it, for example. And it becomes atomic. So if you load and store it, these will be atomic loads. You can even do a compare exchange on it. Okay. It's based on locks, and it fails terribly. In fact, it's basically what it does is if you do it on 64 bytes, it does the right thing. 64 bits, it does the right thing. On anything bigger, it takes a lock and crashes. It performs horribly. But the abstraction is good, because this is, in some sense, what we'd want. We could put one of those blocks into an atomic. We could then load it. We could do our changes, and then we could either store it or compare and swap it, exchange it back. Okay. And we could also add some load, link, store conditional type or instructions to this. Any questions about this interface? I mean, the interface is trivial. Right? And so we want to implement this quickly. I'll mention that beyond hash tables, which is what our original motivation is, there's many other, you can imagine there's many other cases where you might want to load and store multiple words atomically. Okay, I'm not going to go into any of these. Okay, so let's look at how we might implement this. Okay, one way is we could use locks, which is exactly what C++ does, if it's more than one word wide. Okay, that's probably a bad idea. Another is to use indirection. Okay, so it should be clear that we can put a pointer to an object, we can refill it and write it back. This again ruins our, now we have a level of indirection. It actually has a second problem, which is a little bit more subtle, is once we have this level of indirection, we have to manage the memory for that level of indirection, which means we need to announce either in an epoch or in a hazard pointer or something, and this itself will require a memory fence, and that adds additional non-negligible cost to these operations. Another old idea is this sequence lock, which some of you might have seen before. I'm going to go over it quickly. It's a way that's actually quite efficient in the common case, but it's not lock-free. So in the uncommon case, and we'll see that like when you have oversubscription, this approach doesn't work so well. And I'll get to this one in a second. So indirection, well, here's just what you would do. It's sort of the obvious thing, except I mentioned that you do have to protect before you do a load. So this is an indirect load. So I go to a pointer, that's one cache miss. I go to the second thing, that's a second cache miss at least, or maybe I might even have to, chase down a linked list or something, but it's at least 2 cache misses. And it's this protect here, which requires a memory fence of some kind. Okay. And a CAS is, well, it first effectively does a load here, and then it does, the appropriate checks, and then it does just a primitive compare and exchange on the pointer. So you basically update this value on the copy, and then you swap in the new pointer, and then you have to do some more memory management, et cetera, right? And so, as I mentioned, you've got a memory fence and an indirect load. These expensive. You had a question?
Is it like a hazard pointer?
Yeah, like a hazard pointer.
Okay.
Either hazard pointer or an epoch announcement of some kind. Yeah.
Yeah, because like a fence. Are you talking about just like the normal fences? Like if I need all these previous memory operations?
Yeah, the only one I need to guarantee. Yeah, I basically need to guarantee this inside of this protect. I'm going to write to an announcement array, and I need to guarantee that that's in memory.
Okay.
Everyone else can see it before I can move on.
So that's where the fence comes in.
Yeah, yeah. So if I can implement it, with a release, that would be fine too. But I need some kind of.
And you said this is blocking, or you said that
Yes, it's blocking. I'm not allowed to process. I'm not allowed to proceed to this load here until I know that my memory is protected. This is a standard reason why hazard pointers are more expensive than.
No, it's more
yeah.
expensive,
Yeah.
but blocking, you mean not lock-free?
No. Sorry, I didn't mean it that way. I mean, you have to wait until the hardware tells you that this memory's been committed.
It's
Yeah,
costly.
sorry. Yeah, it's costly.
Okay.
I don't mean blocking in the lock-free manner. Sorry. So sequence lock is this cool idea. Is you store with your value a version number, and it can be either. This convention is if it's odd, it's locked. If it's even, it's unlocked, and then you just keep incrementing it. So if you increment an even number, you're effectively locking it, and you increment it again, you unlock it, but now it's 2 greater than it was before. Okay, and so what basically you do, and I'm not going to go through all of this code, but you basically read. What it does is you read the version. Okay, you read the value. Okay. By the way, reading this value for journal types is a little tricky because in C++, this could be a copy constructor and it calls all sorts of funky stuff. So I'm not going to go into that, but you have to be more careful than this. But in the simplest version, you read the value and then you check if the version was either locked, in which case you have to give up, or if the version number changed between here and here, in which case someone wrote something while you were reading this, and since it is in multiple words, you could have like fragments of multiple different writes. So that would obviously be invalid. But if the version number hasn't changed, and if it wasn't locked, you were safe. Okay. And you can then basically do the CAS. I'm not going to go through this in detail, but you basically, somewhere in here, you take a lock. So this is taking the lock here. And then you basically update the value, and then you then you basically unlock by incrementing the version a second time. Okay, so that's the basic idea. This is an old idea. I can't actually find a reference to this idea. It seems to be just one of these ideas that, were out there, and I'm not sure who invented it. Mm-hmm.
Is
advance, right? If things are changing.
That's right.
then
Well,
there's confusion.
yeah, it's definitely not lock-free, because this while loop here, if this guy takes a lock and then gets swapped out, this thing will loop forever, right, until it gets, so it's definitely not lock-free. It can also suffer from starvation if the writers are happening, very fast. These readers could just starve. That's correct. Although in practice, when you don't have oversubscription, this actually works well, and I'll show you some numbers. So the question is, can we get the best of both worlds? So that means avoiding indirection and also being lock-free, or even better, let's say we want to basically, this is the ideal, and we're not going to be able to achieve this, but ideally every single access would be just a single memory access to that, to the cache line that we're looking at, or the cache lines we're looking at, okay? And we wouldn't need any extra memory. Okay, well, this is probably impossible, but this is what we achieve, okay? So what we're going to basically show is that we're only going to access a single cache line, or if the objects are multiple cache line, only the cache lines that objects are on once, with no fences in the case that there's not a race. So if I'm doing a read and no one else is doing a write, I'm just going to zip through there just as fast as sequentially, basically. It's going to be as fast as sequential access. And then on top of that is, well, what if there is a race? Well, first of all, we can ask what the memory is. And then we have two different solutions, one which the memory doubles. Okay, so W is the size of the object, N is the number of objects, so this means we need twice as much. Okay, but we can get weight-free. Okay, so basically in a constant, not only weight-free, but it's a constant number, maybe not one, but in a constant number of memory accesses, we're going to be able to do both updates and reads. Or the other possibility is we actually get near optimal memory, so just N times W, which is all the sequential would need, plus some, this order additional term here, but it's an additive term, and this would be just lock-free and not weight-free. Okay, so I'm going to describe how this works a little bit. And the basic idea is just to combine indirection with version pointers. Okay, and the idea is when there are races, we might have to do this indirection. Okay, because something's happening and I notice it's happening, so I go through the indirection, but otherwise it's going to run just like a sequence lock. And in the sequence lock, basically, if you noticed, it only accesses the version number and the data, and that's all it accesses. There's no indirection or anything like that. Okay, so as long as you put these two near each other on the same cache line, that's good. So the basic idea, and it's much more subtle than this, but is you first try the seqlock method. So you basically read the version, read the data, read the version. By the way, the second time you read the version, you've already got it in cache. So that second read of the version is, in fact, when you read the data, it's already in cache. So the only expensive thing was reading the first version, assuming it's on the same cache line. In the common case, and it turns out that if there's not a race, that will exceed. So if there's no one updating while you're doing that read, that will succeed. Okay. And if that fails, which means there's some update going on that overlaps your execution, then you basically read through the indirection pointer. Okay. Now it turns out it's much more subtle than this. I'm not going to have time to go through the full protocol, but at a high level, that's the idea. And then what about the the CAS? So we want to implement a CAS here. We load the data, okay, as in the previous slide, which itself might either use just the direct version or the indirect version. We check if the old equals the new, and do the appropriate thing. We have to, just like in any of the indirect methods, we have to allocate an extra object. So I should point out that this method still requires an allocate for updates. Okay. And then we install the pointer, Okay, so what this is basically giving us is a backup. So it's saying before I start updating in place this data, okay, I'm going to give anyone that's reading an option to go through that pointer to find the old data, to find the new data. Okay, so now they're going to have this, capability of grab, while I'm doing my things, and it'll take me a long time to fill in this data, right? Because I have to fill it in byte by byte or word by word. And while this is getting filled in, I could go to sleep or whatever, but they can always access it through this pointer here. Okay. And the atomic point here is, and it's actually a little subtle to show this, is when I swap in my this pointer here with a new one, that's the linearization point to prove that this thing is linearizable. Okay. And so, and then if you succeed on this swap in here, then you start copying this data using a seqlock. Now, while you're copying it, you could go to sleep and forever, okay? In which case, from now on, let's say you did go to sleep forever while you're doing this copy, and from now on, people are only going to be able to read through this pointer. This thing is kind of locked. But remember, we said that we're only going to guarantee that you can read through directly if there's not a race. If someone stops halfway through there, then everyone that's reading with them is racing with them. So that's the racy case. And then, then you basically uninstall the pointer and reclaim memory. Any questions about this?
So the pointer version points to the old data?
It points to the new data.
So the new data. So, but you don't try to update that pointer until you've completely filled in the new data in some intro?
No, it's the other way around. Is you first. That probably is. In fact, we looked at the other way around.
Okay.
This one turned out to be simpler. I think you can do it the way you're suggesting. This one here is you first copy new into this allocated object, right? So this is now going to be the new. Then you swap it in here, and you actually, here's the detail, is when you swap it in with an invalid bit. So you put a bit, it requires an extra bit in the high order bit of that pointer. And that invalid bit basically says that anyone that's going to, now from anyone that's trying to read, they both check that the version number is not locked, and they also check that this invalid bit is not set. Does that make sense? Yeah.
So whenever you want to write, you have to write twice and allocate something. Is that not expensive?
It turns out the allocation, you'd think the allocation is expensive. It turns out allocation is very cheap, because it turns out you don't need very many of these. In fact, you only need like p² of them total. Using
you keep it for the thread for.
Yeah, you keep it thread local, and you allocate it on a stack so that all the allocations of cache hits. Okay, all the allocations in free are cache hits. So the allocation of free are cache hits. The copies, the cost of a copy is not the cost of moving the bytes. It's are you doing a cache miss or not? That's the cost of the copy, right? And so the claim is the only cache miss we're doing is on this line, basically. And like I say, all these allocations here can be made to be reasonably fast. Now, they're not zero cost, but they're reasonably fast. In fact, when I show you some numbers, you'll see that the overhead of this is not zero compared to the sequence locks. Yeah.
If the thread that does the update dies, can others still do updates? Or
Yeah, because they can, it turns out you are allowed, if let's say this was invalid, which means this data is in the process of being changed, anyone can update this pointer to another invalid pointer with their thing.
Clever. Mm-hmm.
Right? So this pointer will stay invalid, but it'll be updated to everyone's new pointer. And then eventually when this finishes, it then will validate that pointer.
Okay, just to understand this, so while step 3 is going on, the data has not been changed, pointer has not been changed at all, right? While step 3 is going on, you're just allocating memory and copying newly into it, so everything is fine. But
Yeah.
step 4 is going on. After step 4, other threads can access the new
So this step 4 is the linearization point. That's right. So nothing is visible until then. And if step 4 fails, right, because you could fail the CAS, you basically have to release your memory, and you don't have to try again because you know that the value has changed, and so you can then assume the CAS. You can linearize a CAS either on the old or the new value, and you know one of them would have failed. So you don't even have to try again.
So do you need any CAS alignment here to get the...
Yes, so yes, we align these blocks on cache lines, yeah. Thanks, that's a good point. Any other questions? There are many subtle points where we linearize. I told you where we linearize. Actually, where you linearize on a read is subtle. The read actually linearizes at 2 different places depending on whether you succeed or not on the first try. It's actually not strongly linearizable, this data structure. And because when you actually don't even know after the first linearization point, you don't even know if you've actually linearized there or not. And how do you know which version to use? So the proof of correctness of this is not true. And I should point out, we're in the progress with Siddhartha doing a mechanized proof of this. So we have a mostly mechanized proof of this protocol that shows it's correct. There's an open question. So I gave you an either or. Either it was space efficient or it was weight free. We don't have a protocol that's both. That's both weight free and by the way, the space efficient is the reason it's space inefficient is in one of our 2 versions we keep both values all the time. So there's always 2 values for everything. Okay. And I should point out is not only is that not space efficient, it actually then makes what I said about this allocation unfalse because now we have many more things to allocate, so it's less like, we might not be cache hits. Okay. But the other version, we can, after we install the value, we get rid of the pointer. Okay, so there's only at most p pointers installed at any particular point. Okay, but we don't know how to make that weight free. And the reason why is after you could get into a situation where the read first tries the sequence number version or the direct version and fails, then tries the pointer, and oops, the pointer's now been removed. And now it has to go back. So you might have to loop back and forth between the 2, which will make it lock-free instead of weight-free. Okay. We would love to see a solution to this. Now let's look at some numbers. So this numbers here is just basically a whole bunch of big reads and writes to a variety of an array of big atomics, and we have like 50% reads, 50% writes, size 10 million. K is the number of words. Okay, so that's the size of the block. So it's four words. So that's basically half a cache line. And what we can see here is this red line here is the seq lock. And so you can see seq lock actually does pretty damn well in the normal case. Here is the number, this dashed line here is the number of threads. This is oversubscription. So this is when you have more software threads and hardware threads. And in practice, what this means is some of those software threads are going to go to sleep while they're doing, because the scheduler is going to come in and knock them off. And so they're going to grab this lock, and we're going to get into this situation where the reads are stuck and they can't read. Mm-hmm.
Well, seq lock's only doing well because this is uniform, right? So you're not really getting much. The z equals 0 means it's uniform?
Yeah, it does reasonably well even on the non-uniform case. Even under contention, yeah. Maybe surprisingly, but yeah. And maybe not this well, but reasonably well. This black one is cached memory efficient. So this is basically the overhead of this extra allocations and whatever else we're doing, right? But since it's lock-free, we don't have the problem when we go into this scenario where some of the threads are getting swapped out. In fact, you can see the 3 basically lock-3 algorithms here, the ones which have pretty much straight lines after this position. This one is the seq lock. This one is like a regular lock, and the regular lock is terrible. This one is a C++. which is, by the way, these are fine-grained locks. The C++ has just a lock pool of like 8 locks or something, so it's like really bad. And so this is the sort of forms. Now you ask, well, our whole goal here was to put this in a hash table, right? So, hash table's not just this. There's a whole bunch of other stuff going on, right? There's operator, you have to do comparisons and keys. And so probably the distinction here is going to narrow, and exactly that's what happens. So it's still the case, the seq-lock. So this is basically just the hash table using, I didn't go into detail exactly what method, but think of it like the meta method, where you have some block and you make some updates, okay? So, part of that will be this big atomic where you swap in, the block, make some changes, and then you swap it back out, okay? Compare and swap it back out. So you can see again, the seq-lock suffers under oversubscription, and if you look at these lines, they're effectively just a somewhat narrowing of these lines here because of this other stuff going on, but otherwise they show the same kind of performance difference characteristics. Yeah. So any questions about that? Yeah.
I missed how you made it weight-free. Does the cast not fail?
On the update, if the cast fails, you can linearize before or after.
And does it matter in practice in Google or where you did it? Did people care if it's weight-free or lock-free?
I'm not sure if they care if it's lock-free for being lock-free in itself, but they should care this characteristic is what lock-free gives you, right? Because they are running, in fact, most jobs at Google are not you have a machine and you're running something. Most jobs is you send them to a server and they get run with a whole bunch of other things. And it's nearly always the case that those are oversubscribed because when you send a job, you might not even tell it how many threads you're going to be needing. So it's quite often in their environments where they have many more software threads than hardware threads.
So instead lock freedom, but weight freedom, do you really need it?
Maybe not. So it might be a theoretical question, the one I asked.
We're kind of running a little long here.
Okay, I think this is okay. This is just compared to some real-world hash tables, and yeah. Well, let me just say a few words here. This is a bunch of different loads, and so if you see these other ones, which is a folate, this is the one from Meta, and this is the actual, probably the best other one that's out there. They don't scale, and the reason for this is if they actually scale very well at low Zipfians and low updates, but when you go to high updates and high, they suffer terribly, and you get this sort of performance. Okay, so conclusions, since I've run out of time, is try to avoid locks. Okay, locks have, well, first of all, even under normal conditions, I mean, sequent locks okay, but regular locks, actually, I've never seen them perform, even with read-write locks, they never perform well. Try to avoid indirection. In fact, that was pretty much what whole talk was about. And also try to avoid the memory barriers. So in the common case that I showed, if you do a read and it succeeds in the cache, in the local version, you don't have to take do this memory protection because you're not reading through a pointer. Yeah, so this is basically the result here. You can concurrent load, store, and cache blocks of memory with effectively only one cache miss in the common case. There's many more things that go on with this particular hash table, but I wanted to focus on one particular aspect of it, which was this one. Okay, so that's it.
One more question. I guess we had a fair number during the talk.
So, how far down what does this suggest in terms of when you're designing a data structure, how small do you need to make your atomic objects? Like you wouldn't say, yeah, I'll just get them down to 100 kilobytes and then just use this technique.
No. I mean, a rule of thumb would be 1 or 2 cache lines, I guess. Would be.
Is there any way to measure that or sort of evaluate?
Well, we did in our hash table, we tried both with 1 cache line and 2 and 3 and 4 for the block size, right? Because we can choose the block size, okay? It turned out the one cache line size was the best. And the 2 was almost as good and once you got beyond that. Because if you're going to 3, then every single operation is 3 cache lines of miss, even though you might be only accessing a subset of it. I mean, so that's what this application, but I can't say in general.
But this is just the key, right? Not the data. I mean, this is just the
The key and the data is stored there, yeah.
put a reference to the data to somewhere else, no?
We don't. We just store it right in there. So you can read the key and the data. So like with ints, it's an int key and it's only 8 bytes. With doubles, it's 16 bytes per key value pair. And so you can fit 3 of those on a block plus the header. So that's the best thing we had was basically 3 entries per block plus the header.
So
All right, last question, go for it.
to get big atomics can be supported by hardware, right? There are several papers out there.
You could do hardware transaction. In our paper, we compare to hardware transactional memory.
That was the question. So
Yes. So if you look at our paper, the numbers in there and not so good.
Okay.
Hardware transactional memory is really not a good idea.
All right,
What's
let's
it?
thank Guy again.